very easily, and has been an effort a long time for the materials community, but is still kind of halfway, is to integrate your ability to treat alloys with these tools so that you can do real complicated phase stability. I've done some of this work with Austin Chang, who actually founded the company that makes this software, and you can calculate really complicated, nasty phase diagrams that you really wouldn't ever do ab initio. And they worry about 10 degrees, those kinds of effects, stuff that ab initio is probably not accurate enough to get for a while. But you're doing it primarily from experiment, and we integrated just a few enthalpies of key energies that you needed that they couldn't get experimentally, either due to cost or sometimes due to practical limitations in order to help construct these phase diagrams. So there's a smart give and take between the people who do this kind of modeling and the tools you need to do this kind of modeling and what you can get out of ab initio. And I think it's very valuable to have those communities talking to each other. And there really are issues here. It's not a trivial just translation. We're very focused, for example, on solid solutions. They're great models for solid solutions in the CalFAD community. It's not a totally trivial thing to do from ab initio, though. You have to build these special quasi-random structures, or you have to use fitting, and you have to worry about what kind of error bars you have. There's stuff to think about there, tools to develop, things to automate, and to understand. There's a lot of subtle issues of reference states. If you're going to work with the CalFAD community, you have to have the same reference states they do. They reference to oxygen gas, right? We don't usually reference to oxygen gas, and it's not a nice thing to calculate because it comes out wrong. So you have to fix that, and you have to make sure that you have those reference states consistent with what's done in that community. Other issues about dilute heats of mixing and values, including vibrational effects, including size effects like BJ talked about. There's a lot of issues of end-member calculations. That's one of the key things they're missing in CalFAD that we know how to do. So I think there's a huge opportunity here to integrate what we're doing with quantum mechanical thermodynamic modeling with the sort of tools that people use to construct phase diagrams. But I think you need tools, you need databases, and you need ways to make that integration standardized and easy for people so that people actually do it. A problem I'm interested in, you can see just based on the work I've been doing, is how do I take all that spin energy data and figure out how iron's going to partition as a function of spin. It's interesting to look at the literature on iron partitioning. Every time they found a spin transition, people wrote all sorts of very questionable things about what it meant in terms of partitioning, because they did one little part of the thermodynamic problem in their head or on paper and skipped the full phase stability problem. And you really have to figure out how all the parts are going to fit together. So you really want all the thermodynamics of all these phases and a few more. And then you want to introduce your ab initio spin flip energies and behavior and just look at how it's going to alter the phase diagrams that you would otherwise have that you probably fit without that information. So that kind of integration, I think, could be very powerful for us. OK, so that's pretty much what I wanted to say. Here's a summary, and I'll stop there. Thank you.